Okay, and then 1 mole of or 1 grams mole. So is equal to the element containing 6.023 times weight 1023 atoms. Okay, that is the number of mole. So atomic weights or molar mass for 1 mole of the elements generally has a 12 AMU lah. Okay, so as a relative atomic mass as a carbon atoms. Okay, generally we use carbon 6.0223 times 1023 carbon atom. So if uh, different elements, okay, if you want to calculate, we have to use a carbon atom as a relative calculation lah, relative atomic mass or relative measurement lah. Okay, okay, okay. And then this one is the electronic structure of atoms. If you still remember the configuration or the arrangement of the electrons in orbital. Okay. And predictable elements are classified according to their ground state electron configuration, meaning that the ground state is depending on the energy lah. Okay. Energy of this one, what we call it as electron. Okay, for each quantum number. Quantum number usually we use n. Okay, so a shell quantum number this one. Okay, so actually is the arrangement of electron is not in orbitals. Okay, this one is we call it as not wrong, but this one is like the first theory of the arrangement of electron. Okay, which is suggested or emphasized by the if you remember Bose, the researchers, we call it as Bose models. So it's just arranged along with the orbitals, right? This one, it isn't it? Okay. So it's just like a planet evolve around the sun, right? But actually, it's not like this. The electron actually is a cloud of electron. Okay, it's not around the nucleus and also proton. Okay, so there's the arrangement of we didn't see the arrangement of electron actually. Okay, because it's quite difficult to locate or to know where's the position of the electron because it's moving. Okay, generally if using the quantum knowledge, so we just measure by the probability or the um, okay, probability density, okay, to locate the electron. Okay, if you still remember the how to locate the electrons, uh, if using the if you learn in the mathematics, right, the probability, right? Okay, if this one is the center of the nucleus, so we can locate around the optimum part lah. Okay, electron to from the nucleus, we can know the probability. So there's a existence of the electron. Okay, so if you still remember the what is it, the shell, isn't it? The shells for 1s is a sphere. What else? And then next we have a dumbbell type, and then we have a fan type. This one is S, I think. This one is S, and this one is P. Okay, and then next and so on. Okay, so SP, apa lagi ya susunan? Saya lupa. Check. Okay. Oh, there's a fan type. Fan type. Okay, after that is fan type. After P lah. Okay. So this is the amplitude actually. This is amplitude. The amplitude. Lot of electron for shell S. Okay. Similarly also for dumbbell type. This is the amplitude. Okay. So for example, let me show you the example of the amplitude of the electron, isn't it? So we measure in terms of the wave function using a wave function. Let me share here. Okay, so for example, this one. So we did not, as I told you, isn't it? This one I teach a quantum. So yeah, it's something like that. This is the electron. You see, right? This is cloud of electron. So this is the amplitude. So we say that Bohr model electron is fixed orbit like a planet around the sun and phase distant from nucleus. Actually, is not correct lah. Okay, this is the Bohr model, the right one. And this one is a cloud, charge cloud represent of an orbital. That's why we use a Bohr model. It is the first theory lah. The example of the amplitude of for the electrons we can see here. And this is the example. This one. Okay, this is the S, Kp, and so on. Okay, so this is a hydrogen wave function. Generally, we use this one is only hydrogen wave function. S shell S. Okay, so it's a circle type, round shape. Okay, so this one, this is the probability density how we locate the electron. If you look at here that for the spherical shell, right, S type, this one you can see, isn't it? So it's a this one. Okay, dot here, and this one is dumbbell type. Dumbbell. Okay. So we can locate by using our function. So please remember that one is not exactly the using the Bohr model. Okay, and then if you look at here that as I told you about the position of the location of the electron, right? For each the configuration, not location. Okay, this is another example actually. Jadikannya, let's show. So this is the picture. So one S and then two S, another round shape, right? That one. And then two P dumbbell, three S. So the arrangement is based on the energy state, okay? Which one is the lowest one? And then it's 3P. And then 3D. 3P is a fan. This is 3D. 3D is a fan. Okay. So remember this one is 1S, 2S, 2P, 3S, 3P, 3D, 4S, 4P, 4D, 4F. Okay. So if you look at here that you still remember S, SP, SPD. So until end. Okay. Generally we explain by the Ahbab or Pauli Hansrus. So meaning that 1S, 2S, 2P, 3S, that one is the Ahbab principle. Okay. Pauli exclusion. And then let's see the electron. See, the electron is moving there for 1S and then 2S, another 2. Okay, and then 6 for 2P. So total 8 lah, 2S and 2P. Okay, it's moving right. 3S, another round shape is moving. 3P, another dumbbell type. And then we put another electron. This electron. It's moving. 3D. Fan shape. Okay, we put more. It's moving. That's why there is the amplitude there. Okay, due to the movement of the electron. So that's why it's quite difficult to locate the electrons. Okay, so this is Ahbab principle. Okay, so remember Boleh ingat lagi eh? Okay. So let's we continue. Is it okay? Are you still remember this one? Okay, good. Okay. So let's we continue on the periodic tables. Okay. Oh, already 30 minutes. Okay, so this is the example of periodic table. Actually, is this is I don't know, not updated. If the updated ones, the latest version, I think the periodic table is completed already. Okay, if you know, last 2 years or last 3 years, they have many elements have been found, new elements. Okay, it's already completed. Okay, this one, right? I think some missing element already fails, like nihoniums, which is found by Japanese researcher. Okay, so that is one of the element, the new elements already included in the periodic tables. Okay, so the periodicity concept map, what we can found from the periodic tables, we refer to the trend in properties of the atoms as one move in various direction within the periodic tables. What we can know is the properties and trends to know ionization energies. What else? Electron affinities. This is important for the bondings, especially the electronegativity. Electronegativity, yes. And then the atomic ready. Okay, atomic ready is different from the left to the side and from top to the bottoms. Okay, the atomic ready is different. So the strength of the when to form the bond is actually is different. Okay, for example, maybe if group 1A and 2A, 1A 2A is alkali and alkali metals. So if with the group of 6A or 7A, they can form the ionic bonding. Okay, so because of high very difference of electronegativity, that's why they can form the ionic bondings. Actually, the difference in the electronegativity, we can distinguish or we can differentiate type of the bondings. For example, what is it? We can differentiate between ionic bonding and also what is another one? Valence, right? Valence bondings, or maybe another one is a metallic bonding. Okay, so we can differentiate actually. Okay, maybe between 6A we can form the covalent valence bonding. Covalent bondings. Okay, we can form a covalent bonding. Okay, there's a measurements the electronegativity between 0 to 4. Okay, so atom ready, which are defined in different ways for the metallic covalent bonded atom and atom in ionic solids. So this is the information we can get. So look at here that from the left to the right of the periodic tables and from the bottom to top, more non-metallic character and more negative electron affinity and increased ionization energy. So you have to remember that. Okay, from left to right, from bottom to top. Okay, and from right to left, from top to bottom is the opposite, which is more metallic character. Of course, because that's why we call it as 1A and 2A is as alkali and alkaline earth metals, 1A, 2A, because it's more metallic character. Potassium, what is it, calcium, magnesium, okay, that is a more to metallic character. Okay, more non-metallic from left to right. So from, for example, 6A, 7A, Cl, O2, okay, and noble gases. This is a non-metallic. Okay. Okay, trend in atomic size. If you look at here that the size of atom is measured in terms of radius. Okay, it depend on the electronic structure. Okay, so meaning that if you still remember the model, the orbital, right, increasing in the shell, okay, will increase as that increase. So meaning that the electronegativity is increased. Okay, so metallic radius, if you look at here, half the distance between the nuclei of two adjacent atom in a metallic crystal. Or for example, natrium, sodium and sodium. Okay, potassium and potassium. Okay, covalent radius. This one is the, what is it, bonded together in a molecules. Okay, How to differentiate between covalent radius and material is depending on the electronegativity difference. Okay, and similarly also for ionic radius. Okay, we can differentiate. So ionic radius, for example, is sodium and chlorine, the effective radius of ions in solid. Okay, and van der Waals we can consider as the secondary bondings. Okay, so this is not chemically bonded like a primary, but it's mostly like close contact, or yeah, this one is just, we call it as, it's like a touch, okay, we touch between two atoms or two molecules. So that's why we call it, but are presumably in a contact. Okay, okay, and then this one is of the examples. They have a contact between two molecules. Okay, we call this van der Waals. Very not really strong lah. There's a strong, there's a two type of the secondary, fluctuate and permanent. Permanent, I think, is like a hydrogen bonding. Okay, so this is the various atomic radius. We look at here, van der Waals, covalent diameter. Covalent is sharing sharing the electron. This one is a van der Waals is touch. Metallic is a more like between two metals. Okay. Okay, in terms of ionization energy, okay, the energy needed to remove an electron from atom. For example, group 1A and 2A. This is alkaline and alkaline earth metals. Okay, they're readily to lose the electrons to become the cation, right? So it's going to be reduced the size of the atom, okay, because it's transfer the electron. Okay, for example, this one, lithium, sodium, and potassium. So the outer orbital is for lithium is 1, so it's readily to transfer to. So for example, if we want to form the lithium chloride, so it's ready to transfer one electron. Okay, so it's going to be decreasing. So from left to right, for example, alkali earth metals, and to the right is going to be reduced. No, from top to bottom. Okay, ionization energy will be decreased. Okay, for example, this one, right? Lithium, sodium, potassium. Okay, this is decrease in ionization and energy because increase in the orbitals number. Okay, okay. So in terms of affinity, so they're readily to accept the electrons to become an ion. Okay, meaning that the group 6A and 7A. Okay, so electron affinity increase from top to bottom of the periodic table and from left to the right. Okay. Okay, that one is in terms of electron affinity, as well as electrons, what is it, ionization energy lah. Okay, so let's see the oxidation number. If you look at here, that uh, the number of electron an atom can give up through ionization process is called a positive oxidation number. If you give sama lah, macam it's same like almost similar like electron and ionization affinity. So if gain is going to be negative oxidation number. Okay, 0 is mean the neutral substance. Okay, or atom like O2, O3, P4, that one is the oxidation number is equal to 0. Okay. Okay. So another one important things we can read from the periodic table is the electronegativity. Actually, from left to the right, it's going to be increasing the electronegativity. It's much higher. We measure in a numerical scale of 0 to 4. Okay. So from this electronegativity, okay, we can predict the type of the bonding actually. Okay. So look at here that electronegative atom tends to attract bond readily accept electron is anion. Oh, sorry. Just now is what I said. If accept is an ion. Yeah. Accept electron is an ion. And then to give the electron we is become to form the cation. So meaning that the is become positive oxidation number, and the size of the radius will be decreased. Okay. So this one, okay, electronegativity value are useful in predicting the type of the bonding. Okay, most likely between two atoms. So we can predict either covalence, ionics, or metallics. Okay, so this is very, very important. So this is the example, the picture or the clear picture how the electronegativity can be predicted from the periodic table. Okay, from lowest electronegativity to the highest electronegativity. Okay, is it clear, right? Okay, so let's see the difference between metals, metalloids, and also non-metals. We can see from the periodic tables. Okay. So the elements actually in the periodic tables we can classify into metals and also non-metals. Okay, and metalloids we can divide into a metal or non-metal. Okay, so metalloid is actually the behavior. It can act as a metal or non-metal. Okay, so one of the example is a reactive metal. 1A to A. Okay, here is this is reactive metal. Okay, this is reactive metal. I have a low ionization energy and for the electron affinity is a low lah. Okay, for to accept the electron, right? Okay, so actually it's tend to lose the electron or we give the electron. Okay, reactive non-metal generally this one we call it a 3, 4, 5, 6. This one is electron. Reactive non-metal. Ionization energy increase, right? Higher, right? This one, if you still remember from the previous slide. And affinity is also is high. Okay, so this one can accept electron. Okay, group 6A and also 7A lah. This one we call it. Right? This one is more to metal. Okay, what else? Metalloids. Metalloids is 3A, 4A, 5A. This one is metalloids. Can behave like metal or non-metal. Boron, carbon, okay, aluminum, silicon. Okay, so this is have an intermediate electronegativity. Uh, Boron, I think this one is a metalloid. Okay, and the rest is a metal. This one is metal. Metalloid. Carbon is non-metal. This one is metalloid. Right. Silicon, plumber is metal. See, so it's a mixture, right? 5A also is a mixture metal, metalloids, and non-metals. Okay, another important classes in periodic table, this one, noble gas. Okay, this is a stable. Okay, generally if we do the reaction, uh, we can use helium to purge the oxygen, okay, or argon. Nitrogen also can, nitrogen, but need to in the molecule, nitrogen. Okay, but this one is expensive if you want to buy the non-ruthenium. So this one is non-reactive. You have to remember this one is non-reactive, no electronegativity. Okay, so generally it's complete, that's why it's stable. Oh, this one is the explanation. Okay, I already explained. You can read this one from the reactive metal, reactive non-metal, and also noble gas. Okay, special case, right? Complete valence S2 to S6 already 8, right? Configuration, ionization, and non-electricity affinity. Okay, any question about the how to about the information that we can get from the periodic tables? Ada soalan tak? Any questions? So this is the example problem. Any questions? Any question from participant, audience? Okay, students? Clear? Okay, if it's clear, uh, this one, right? Example problem 1. Let's do together. 1S. The most abundant isotope of iron. Ferrum. Ferrum lah, iron lah. Okay, that's the isotope. This is the isotope. Transition metal is another case lah. That's another group lah, transition metal ni. And there's a lantanet and another group, right? That's why we're gonna, this one is transition metal lah. 3B until berapa ni? Saya tak nampak ni. Until up to here lah. This is B group. Okay, they are on transition metal. And lantanet another one, what is it? Check. Actinide. Lantanet, actinide, another group lah. Okay, this one. Cerium, PR, what else? Palladium platinum is really expensive if we want to use as a catalyst. This one is the transition metal. Okay. This is in the transition metal. Okay. Another group lah. Focus. We're just focusing on the, what is it? 1A group. Okay. Find the average atomic mass of the iron. This is the isotope, right? What is relative atomic mass of iron? How many atoms are there? How many are there in 1 gram? And then what are the mass in gram of one atom of ferrum iron? Based on the answer in part E, what is the mass in the gram of 1 AMU? Can you do and paste in the Jamboard? So this is the, I give you, we recall it back. Do you still remember? I give you around 5 to 10 minutes. This is the link for the Jamboard. Paste your answer. Go to page 3. Chapter. How you do the calculation? Show me the calculation, not only answer. You can write and put a picture. Okay, A, B, C, and D. E, F.
Doctor, page 3, right?
Yes, page 3. Chapter 2, atomic structure. I wrote there. Oh, calculate just guna ni je. Apa ni? Sticky note. I think you can write in the, edit, in the A4 paper and take picture is much better. Okay. So 55.84. Okay. What is the unit? I don't know what is the unit.
Grams per mole.
Grams per mole. What is the unit? Nabila Wahyu.
AMU right after.
Yes. Should be AMU. Average atomic mass. Look at back the mass of atom. Yeah. Should be AMU.
The relative atomic mass should be the same, right?
Relative?
The B should be the same, isn't it?
Yes. But what is the unit?
Um, Grams per mole.
It's just a gram. How do you get the mole? Just the gram.
Just gram.
Mm-mm. It's based on the carbon atom, right? Okay. Okay. Then B already is 55.8 grams. How many atoms are there? C? How about C, D? How many atoms in 55.849 gram of ferrum or iron? So it's the same, right? Same like relative to the carbon. Relative to carbon. What is it? It should be 6.023 times 1023 lah. Okay.
It's roughly 6.022 into 10 to
Yeah,
the power 23.
yeah. But how about if 1 gram? Just now if 51, right? 55. But how about 1 gram? So just based on the ratio lah, you can calculate.
1.078
Yeah. Okay,
to the
1.7.
power 22.
Yeah. Okay. So E mass in gram of one atom of Fe. So just 55.849 divided by 6.023 times 1023 lah. Okay, so you can get in gram gram of one atom. Okay. So in AMU, okay, since for 1 grams from the E, right, one atom is equal to 9.277. Okay, so just divide by 55.849 in A. So meaning that you have E, right? Here. So the answer in E divide by A, because A in AMU. Okay, and this one in gram. So you can get answer for M. Okay, easy, isn't it? Okay, so there's another tutorial actually. Till we almost finished. So short. How about this one? 100 gram alloy of nickel and copper consists of 75% of copper and 25% of nickel. What are percentage of copper and nickel atom in this alloy? Okay, can you find the answer? So first you have to determine the what is it? The atomic weight for each element or for each atom. For copper, how much is the atomic weight? Okay, kalau kita panggil, if for molecules we call it molecular weight lah. For atom is we call it atomic weight. And then you have to determine the number of gram mole for each atom. So meaning that since 75% per 100 gram is if you times with 100 gram with times with the 75% of the copper, meaning that you can get 75 gram, okay, of copper. So you have to divide it by the atomic weight. Okay, and then similarly also you do for the nickels, and then get the total what is it, number of mole. Okay, so number of mole copper divided by total mole of copper and nickel, so you can get the atomic percentage. Can you calculate? Give me the answer. Give me the answer. Problem number 2, okay? This one. It's easy, this one. Yeah. Okay. How many percentage? Copper in alloy and also nickel in alloy. Atomic percentage. Please give me the answer. Oh, almost 11 o'clock. 5 minutes, faster. Five minutes, faster. .5 and 26.5. Okay, that's correct. Okay, so you have to determine mole number for each atom. Okay, and then for copper and nickels. Okay, sum of the mole number of copper and also nickels, you can get total mole. So number of mole copper divided by total mole, you can times with 100, you can get 70.5% for copper. This one. And then for nickel, number of mole nickel, mole in mole. You have to convert to mole and then total mole. So you can get percentage lah. Okay. So meaning that your atomic percentage is in mole percent, since you already converted to mole. Okay. Because from the question it's just in the weight percent, right? Okay. So that's all. Thank you very much. For the example problem 3, you can do. I already upload on this what is it? PowerPoint slide in the e-learning. Oh yes, okay. Thank you. Already uploaded. Okay. So maybe by next week lah, tomorrow, no class, 2 hours of class. I think last week or last 2 weeks also we have to cancel. But it's okay. So maybe by next week we can finish this part. So mainly we are covering the type of the bondings of primary and secondary. So I think you can read by yourself to get some brief picture about this part. Okay. So that's all for today. For those who still not scan the mana QR code What's the QR code Check. Sekejap Please scan the QR code for the attendance. Sekejap Okay, that's all. Thank you very much. Let me.
Thank you, Doctor.
Okay, thank you. Thank you very much. See you next week. So this is the QR code for the attendance. Please scan. See you.
Yeah.
Okay. You done okay? So thank you very much.
Doktor,
Yeah.
nak tanya, buku
Hmm.
apa yang sesuai untuk buat latihan?
Buku apa?
Ha,
Material Science lah. Yang hari tu lah. Yang saya ada tunjuk masa introduction class tu kan?
yang Fundamentals of Material Engineering tu je.
Foundation.
Oh, Foundation, sorry.
And also Mechanics of Material tu kan?
Ha,
Yang part tu. Foundation ataupun Foundation of Material Science and Engineering also ataupun apa saya lupa Callister yang dia punya author Materials Engineering lah, Material Science lah. Sama je tu. Tapi different author lah. Material Science. Callister saya rasa.
okay.
Buat tengok balik lah dalam saya punya yang slide sebelum tu, yang introduction class tu.
Okay,
Okay.
terima kasih doktor.
Okay.